Hello students, welcome to another video of number theory. Today we are going to discuss some properties of Legendre symbol. So today's topic is properties of Legendre symbol. Properties of Legendre symbol. So we will take that properties in theorem. The theorem says that let P be an odd prime, P be an odd prime, and this A, B be integers, such that these both A and B are relatively prime to P, such that both are relatively prime to P. That is GCD of A with P and GCD of B with P is equals to 1. Then we have the following properties. First property is Legendre symbol of A and P. Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P. Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P. Now in the problems, if we are going to find the Legendre symbol of A and P, we are just going to take the A raised to P minus 1 by 2, and after taking the A raised to P minus 1 by 2 under modulo P, we get some residue, and that residue is either 1 or minus 1, and which is our Legendre symbol of A and P. Second property, Legendre symbol of A and P into Legendre symbol of B and P is equals to Legendre symbol of A into B with P. Legendre symbol of A and P into Legendre symbol of B and P is equals to Legendre symbol of AB with P. Third property, if A is congruent to B mod P, then Legendre symbol of A and P is equals to Legendre symbol of B and P. Fourth property, if GCD of A and P is equals to 1, then Legendre symbol of A square with P is equals to 1. Also Legendre symbol of A square into B with P, Legendre symbol of A square B with P is equals to Legendre symbol of B and P. And the last property, Legendre symbol of 1 and P is equals to 1, and Legendre symbol of minus 1 and P is equals to minus 1 raised to P minus 1 by 2. Now we are going to take the proof of this theorem or the proof of these properties. First property is Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P. We have given that P is an odd prime and GCD of A with P is equals to GCD of B with P is equals to 1, that is A and B are relatively prime to P, and first our claim is this Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P. So first of all, write the given things. Let A and B are integers such that they are relatively prime to P. First claim is Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P. So to prove this result, we have two possibilities of Legendre symbol of A and P, which are either 1 or -1. Since here P is odd prime and A is relatively prime to that P, so P doesn't divide A. So third possibility is not so. There are only two possibilities. First possibility is Legendre symbol of A and P is equals to 1, and second possibility is Legendre symbol of A and P is equals to -1. So here we are going to consider two cases. First case, if Legendre symbol of A and P is equals to 1. Now if Legendre symbol of A and P is equals to 1, then by definition of Legendre symbol we have the congruence x square is congruent to A mod P has solution. Therefore this congruence x square is congruent to A mod P has solution. Suppose that solution be some x naught. This implies x naught satisfies this congruence, that is x naught square is congruent to A mod P. Now raising the power of both sides by P minus 1 by 2, we will get this implies x naught square to the power P minus 1 by 2 is congruent to A raised to P minus 1 by 2 under modulo P. Since P is odd prime, P minus 1 is P minus 1 by 2 is an integer. So A raised to P minus 1 by 2 is congruent to x square. So this becomes 2 gets cancelled. X naught to the power P minus 1 is congruent to A raised to P minus 1 by 2 under modulo P. So this is suppose equation number 1. Also we have GCD of A and P is equals to 1. P is an odd prime and GCD of AP is equals to 1. So we can use Fermat's theorem as GCD of A and P is equals to 1. Therefore by using Fermat's theorem we can write A raised to P minus 1 is congruent to 1 mod P. So by Fermat's theorem we have A raised to P minus 1 is congruent to 1 mod P. This suppose equation number 2. From this equation number 1 we have A raised to P minus 1 by 2 is congruent to x naught raised to P minus 1 under modulo P. From equation 2 we have A raised to P minus 1 is congruent to 1 mod P. So instead of doing equation 2, just raise the power of both sides by 1 by 2, we can write A raised to P minus 1 by 2 is congruent to 1 raised to 1 by 2 is 1 under modulo P. So this is suppose equation number 2. Now from equation 1 we have this x naught raised to P minus 1 is congruent to A raised to P minus 1 by 2 under modulo P, and from equation 2 we have A raised to P minus 1 by 2 is congruent to 1 mod P. So combining equation 1 and 2, equations 1 and 2, we get A raised to P minus 1 by 2 is congruent to x naught raised to P minus 1, and this again congruent to 1 mod P. Just combining for equation 1 and 2 we can write here this. So in the first case we have considered Legendre symbol of A and P is equals to 1. So instead of 1 I can write Legendre symbol of A and P here. So this will give A raised to P minus 1 by 2 is congruent to this Legendre symbol of A and P under modulo P. So here using the result A is congruent to B, then B is congruent to A, I can write Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P. Hence the proof of first case. Now in the second case, if Legendre symbol of A and P is equals to minus 1, Legendre symbol of A and P is equals to minus 1 means the congruence x square is congruent to A mod P has no solution. Therefore we are going to prove this is say like the proof of Wilson's theorem. So therefore for each j such that j varies from 1 to p minus 1, we can associate an integer, suppose I. We can associate an integer I such that this I is again in between 1 to p minus 1, such that their product I into j is congruent to a mod p, where I is not equals to j. If I is equals to j, then we get I square is congruent to a mod p, and that I will be the solution of this congruence. Here for I not equals to j, I can write I into j is congruent to a mod p. Here I not equals to j, since if I is equals to j, then we get I square is congruent to a mod p, and this implies x is equals to I is solution of x square is congruent to a mod p. So this will give the contradiction to A is quadratic non-residue, that is Legendre symbol of A and P is equals to minus 1, which is contradiction to A is quadratic non-residue, or which is contradiction to Legendre symbol of A and P is equals to minus 1, quadratic non-residue. So the integers 1 to up to p minus 1 can be paired, that is I in the form of I and j. Then the integers I and j, that is varies from 1, 2, 3 up to p minus 1 can be paired such that I into j is congruent to A modulo p. In the second case, till now we have taken the the Legendre symbol of A and P is equals to minus 1. So by using definition of Legendre symbol, we can say that this congruence has no solution. X square is congruent to A modulo p has no solution, that is A is quadratic non-residue. So if this congruence has no solution, so we can pair the numbers 1, 2, 3 up to p minus 1. We can pair these numbers in the form of I into j, where I and j are not equal. If I is equals to j, then we will get the solution of the congruence, which is not possible. So we can pair the I and j such that I into j is congruent to A mod p. So we have this pairing I into j is congruent to A mod p, and these I and j are in between 1 to p minus 1. So multiplying these all congruences, that is multiplying all those pairings, so there are exactly p minus 1 by 2 numbers. So p minus 1 by 2 pairings, multiplying all these pairs, we will get 1 into 2 into 3. Just multiplying these all congruences, these all p minus 1 by 2 congruences, and rearranging these numbers, we can write 1 into 2 into 3 into up to p minus 1 integers, which is congruent to A into A into A into A. This, suppose this pair 1 into 3 is congruent to A mod p, again the pair 2 into 4 is congruent to A mod p. So all the pairing, multiplying all these pairings, I can write this A under modulo p, and this A will occur p minus 1 by 2 times, since pairing these numbers, these are p minus 1 numbers, and pairing all these numbers. So for each pair there are 2 elements, so there are exactly p minus 1 by 2 pairs. So this A will occur p minus 1 by 2 times. So this will give this 1 into 2 into 3 into up to p minus 1, I can write it as p minus 1 factorial, and this A will occur p minus 1 by 2 times. So, taking a to the power p minus 1 by 2, we will get p minus 1 factorial, will get p minus 1 factorial is congruent to a raised to p minus 1 by 2 under modulo p, and by Wilson's theorem we have p minus 1 factorial is congruent to minus 1 mod p. So, I can write minus 1 is congruent to a raised to p minus 1 by 2 under modulo p. This is by Wilson's theorem. By Wilson's theorem. And in the second case, we have considered the Legendre symbol of a and p is minus 1. So, I can write Legendre symbol of a and p instead of this minus 1. So, we will get Legendre symbol of a and p is congruent to a raised to p minus 1 by 2 under modulo p. Hence, the proof of first property. In the proof of first property, we have seen two cases, in which first case is Legendre symbol of a and p is equals to 1. If Legendre symbol of a and p is equals to 1, then this congruence has solution. Suppose that solution will be x naught, then x naught satisfies this congruence, and raising the power of both sides by p minus 1 by 2, you will get equation number 1. Also, GCD of a and p is equals to 1. So, by using Fermat's theorem, we will get a raised to p minus 1 is congruent to 1 mod p, and raising the power of both sides by 1 by 2, I will get this. So, combining equation 1 and 2, you will get this. So, Legendre symbol of a and p is equals to a raised to p minus 1 by 2 under modulo p. In the second case, if Legendre symbol of a and p is equals to minus 1, then we will prove this result similarly as we have proved in Wilson's theorem, pairing the integers which are in between 1 to p minus 1 I and j in such a way that they are not equal, that is I and j are not equal, then we will, and multiplying these pairings, these all p minus 1 by 2 congruence, we will get 1 into 2 into 3 up to p minus 1 is congruent to a raised to p minus 1 under modulo p, and here Legendre symbol of a and p is equals to minus 1. So, writing a Legendre symbol of a and p instead of minus 1, we will get our result. Now, the second claim is Legendre symbol of a and p into Legendre symbol of b and p is equals to Legendre symbol of ab with p. The second claim is Legendre symbol of ap into Legendre symbol of b p is equals to Legendre symbol of ab with p. Since we have GCD of ap, that is a and b are integers which are relatively prime to p. So, we have Legendre symbol of ap with Legendre symbol, GCD of ab ap and GCD of b with p is equals to 1. So, we can use the result, the GCD of am is equal to GCD of bm is equals to 1, then GCD of ab with m, that is GCD of ab with p is equals to 1. This is by using the result, GCD of am is equals to GCD of bm is equals to 1, then GCD of ab with m is equals to 1. Using that result, I can write here. Now, using the first property, therefore, by result 1 or property 1, which is property A, I can write here GCD of AB with P is equals to 1. So, I can write Legendre symbol of AB with P is equals to AB raised to P minus 1 by 2 under modulo P. Since the first property says that Legendre symbol of AB, Legendre symbol of AP is congruent to A raised to P minus 1 by 2 under modulo P. So, if GCD of A and P is equals to 1, then we can write this. So, here GCD of AB with P is equals to 1. So, I can write Legendre symbol of AB with P is congruent to AB raised to P minus 1 by 2 under modulo P. So, rewriting this such that Legendre symbol of AB with P is congruent to. So, AB raised to P minus 1 by 2 gives us A raised to P minus 1 by 2 into B raised to P minus 1 by 2 under modulo P. Also, this Legendre symbol of AP is equals to 1 and Legendre symbol of BP is equals to 1. So, using the first property on these two, since Legendre symbol of AP is equals to 1 and Legendre symbol of B and P is equals to 1, therefore, by property 1, we can write A raised to Legendre symbol of A and P is congruent to A raised to P minus 1 by 2 under modulo P, and Legendre symbol of B and P is congruent to B raised to P minus 1 by 2 under modulo P. Suppose this is equation number star. Is putting this equation number, suppose 1 and 2 in equation star, we will get, therefore, equation star becomes, or we can rewrite equation star as Legendre symbol of AB with P is congruent to A raised to P minus 1 by 2 is congruent to Legendre symbol of A and P, and B raised to P minus 1 by 2 is congruent to Legendre symbol of B and P under modulo P, or that is Legendre symbol of AB with P is equals to Legendre symbol of A with P into Legendre symbol of B with P. Hence, the proof of second property. Now, to prove the third property. Third property is, if A is congruent to B mod P, then Legendre symbol of AP is equals to Legendre symbol of B and P. So, in the third or C claim, here given that A is congruent to B mod P, also we have GCD of AP is equals to 1, GCD of B and P is equals to 1, and our claim is GCD, Legendre symbol of AP is equals to Legendre symbol of B and P, as this A is congruent to B mod P. So, increasing the power of both side by A raised to P minus 1 by 2, we will get A raised to P minus 1 by 2 is congruent to B raised to P minus 1 by 2 under modulo P. This is by raising the power of both sides by P minus 1 by 2, and from the first property we have A raised to P minus 1 by 2 is congruent to Legendre symbol of A and P, and B raised to P minus 1 by 2 is congruent to Legendre symbol of B and P under modulo B by result 1, or by property, that A property. This will give the Legendre symbol of A and P is equals to Legendre symbol of B and P. Now, the fourth result, fourth claim is GCD of A and P is equals to 1, then A square, Legendre symbol of A square is A square with P is equals to 1, and also Legendre symbol of A square into B with P is equals to Legendre symbol of B with P. Now, to prove the fourth result, here our claim is Legendre symbol of A square with P is equals to 1, and Legendre symbol of A square B with P is equals to Legendre symbol of B with P. Since we have given GCD of A and P is equals to 1, this will give GCD of A square and P is equals to 1. Since GCD of AP is equals to 1, GCD of AP is equals to 1, and using the result GCD of AM is equals to 1, which is equals again GCD of BM is equals to 1, then GCD of AB with, so similar result using this result. GCD of AM is equals to GCD of BM is equals to 1, then GCD of AB with M is equals to 1. Here a is equals to a and b is equals to b, then ab is a square. So GCD of a square with p is equals to 1. Therefore, by result a, we can write a square to the power, Legendre symbol of a square by p is congruent to a square to the power p minus 1 by 2 under modulo p. So, just simplifying this, we will get a raised to p minus 1 under modulo p. Legendre symbol of a square with p is congruent to a raised to p minus 1 under modulo p. But by Fermat's theorem, we have a raised to p minus 1 is congruent to a raised to p minus 1 is congruent to 1 mod p by Fermat's theorem. So, thus we have Legendre symbol of a square with p is equals to 1. This is Legendre symbol of a square with p. So, also we have to prove that if Legendre symbol of a square into, also we have to prove that a square, Legendre symbol of a square into b with p is equal to Legendre symbol of b and p. Now, consider, suppose this is equation number 1, or suppose this is equation number a, capital A. Consider, to prove this Legendre symbol of a square b with p is equals to Legendre symbol of b and p, consider the left hand side. Consider Legendre symbol of a square b with p, which is equals to, but by the result, second result, we have Legendre symbol of ab with p is equals to Legendre symbol of a with p into Legendre symbol of b with p. So, here Legendre symbol of a square into b with p, we can write it as Legendre symbol of a square with p into Legendre symbol of b with p, and from equation number a we have this Legendre symbol of a square and p is 1. So, we will get the result Legendre symbol of a square into b with p is equals to Legendre symbol of b with p. Hence, the proof of fourth property. Now, the fifth property. Fifth property is Legendre symbol of 1 and p is equals to 1 and Legendre symbol of minus 1 and p is equals to minus 1 raised to p minus 1 by 2. So, fifth claim is Legendre symbol of 1 and p is equals to 1 and Legendre symbol of minus 1 and p is equals to minus 1 raised to p minus 1 by 2. Since we have GCD of 1 and p is clearly 1, since p is prime number and 1 is 1, that is 1 is, and GCD of a 1 and p is equals to surely 1. So, by using result 1 or result A, we get Legendre symbol of 1 and p is equals to 1 raised to p minus 1 by 2, 1 raised to p minus 1 by 2 under modulo p, and we know that 1 raised to any integer is 1 under modulo p. This will give the Legendre symbol of 1 and p is equals to 1. Also, since GCD of minus 1 and p is 1, since the 1 is the only integer which divide minus 1 and that prime. So, GCD of minus 1 and p is clearly 1. So, therefore, again by result A, we can write Legendre symbol of minus 1 and p is congruent to, sorry, here congruent sign is congruent to minus 1 raised to p minus 1 by 2 under modulo p. So, we can write Legendre symbol of minus 1 and p is equals to minus 1 raised to p minus 1 by 2. Hence the theorem, that is all the property, proof of all the properties.